My name's Dan Parry-Williams. I'm Director of Engineering Design at McLaren Automotive, and I'd like to talk to you today about a man called Sir Isaac Newton. Sir Isaac Newton, who is considered to be the father of modern physics, gave us, crucially, his laws of motion. The second law of motion states F equals ma. F is applied force, m is mass, and a is resulting acceleration. And since everything we do at McLaren is moving, it fundamentally affects everything that we do. So we can clearly see the simple relationship between low mass and high acceleration, and why mass is so fundamentally important to car performance. And this driving principle has underpinned pretty much all high-performance road cars. Here at McLaren, it's just part of our DNA. It's something that is fundamental to everything that we do. And the way in which we do it is principally in four different ways. First of all, we have to design light. The most effective way to save weight is to never add weight in the first place. And the best way to do that is to make sure that when you design a part, it has multiple functions. So one part doing 3 or 4 jobs is much more efficient and means that you can just delete all of those other parts before you even add them. Secondly, advances in materials science and the application of new materials technology is really important. Thirdly, advances in simulation techniques. Computer simulation is now so robust, so reliable, that it more or less displaces most of the testing that used to be done. And finally, and probably most importantly of all, teamwork. Because in an increasingly complex world with lots of different people involved in processes, it's absolutely vital that everybody is pointing in the same direction, understands fundamentally what we're all driving for. This car represents a really good example of component integration. It's a McLaren Formula One car from 1969. And in the 1960s, the monocoque chassis was developed. Prior to that, race cars had a separate chassis frame. But here, the chassis is actually the bodywork. That's the structure of the car. It's riveted aluminium. Actually contains the fuel tanks as well, and the seat is incorporated into the structures. So in summary, this is a really good example of removing all of the extraneous parts, reducing the design to its essence, incorporating as much function into just one part. Another good example is the door of the McLaren Senna. So the principle we adopted with the door of the Senna is that there's no interior trim. The exterior surface is really extreme in the case of the Senna. The very short dropping glass means that we have a very small and lightweight glass lift mechanism. And because it's so small, it meant that we could effectively cut a hole right the way through the door in most of the lower part of the door, which we can close off either with a piece of glazing or a thin piece of carbon fibre. This makes the structure even more rigid. So it is in fact the lightest and most rigid door we've ever made. The suspension in the 1960s sports car is essentially fabricated steel. Suspension in a modern day Formula One car is moulded carbon fibre. And even within the same component, parts of that wishbone, as we call it, is rigid, extremely stiff, extremely light, and part of it is flexible. So there is in fact no pivot that has to be bolted onto this wishbone. At the end of the leg of the wishbone, it tapers down to a thin section and it literally flexes. The first carbon monocoque chassis produced by McLaren was the MP41 in 1981, and the first carbon chassis road car was the McLaren 12C, and every car we've produced since that first car has a carbon monocoque chassis. So we've just been looking at suspension on a Formula One car. This is a lovely little object. It's a machine from solid titanium, a rear upper wishbone mount from a Formula One car of about 20 years ago. It's rather dinky, it's all pocketed out, so it's as light as it can possibly be, and titanium is an interesting material. Correspondingly, this is the wishbone mounting of a current McLaren road car. You can see there are similarities, the fixings here. These parts are actually aluminium in order to try and save as much weight as possible. They're very much larger, and a lot of the reasons for the size of this part compared with that part relate to the weight of the cars themselves, but also the durability requirement of the car. So when you're designing for lightweight, normally you're designing for something to be as rigid as it can be and as light as possible, or as strong as it can be and as light as possible. In this case, we can compare the difference in weight and rigidity. You'll have to take my word for it with the weight, but this is an aluminium ring, and if I squeeze this, I get a good sense of how rigid that material is. That weighs about 7 grams. This component here is stainless steel. It weighs 3 times the weight of this one, but it's also 3 times more rigid. So depending on the application, this might be a better choice than that, or that might be a better choice. But in terms of the overall, what we call specific stiffness, very much the same. This part is titanium, same material as this. It's about 30% heavier than aluminium, getting on for the strength of steel, and that means in some applications it's a much more efficient solution, and certainly a really good way of saving weight where you need a high degree of strength. Of course, modern cars, whether they're racing cars or road cars, are extremely complicated. There are lots of people involved. Everybody needs to be working in the same direction, needs to be conscious of the overall goal. The ability for people to work together and the opportunity for people to work together is fundamental to the success of weight saving, because teamwork is also underpinning everything that we do.